Okay, welcome to page 3. Hopefully the bottom half of this will be a little bit easier for you. But we're going to start off with some more general solutions. Remember, this is going to be a plus C idea, the general solution, because we don't have an initial condition. Okay, so we're going to move the dx over to this side because your first step is to separate. So we're going to have e to the 2y dy equals x cubed times dx. Okay, so then we have separated. Now we're going to integrate. Remember, the integral of e to the y is itself. So we have e to the 2y. Okay, but something is missing because in order to have, it is its own derivative. So we would have to have a 1/2, right? Because you're going to take the, if we were to derive e to the 2y, that would be e to the 2y times 2, right? So we should have a times 2 out here for that. When we take the derivative, this becomes a 1. So 1/2 will take care of that. So 1/2 e to the 2y on the left side, and on the right side, x to the 4th over 4 plus c. So all we really have to do is solve this equation for y, which happens to be in a denominator. So maybe not as easy said than done than said. So we'll multiply everything by 2. That's pretty easy. So we can get rid of that 1/2. So e to the 2y equals 1/2 of x to the 4th plus some other value c, right? Maybe c sub 2. Maybe you like the subscript method. It really doesn't matter that much. Okay, but now we're going to get rid of our e by natural logging everything, right? Both sides. So this is gone, leaving me with a 2y equals the natural log of 1/2 of x to the 4th plus some c value. And then divide everything by 2, right? That's a perfectly fine answer. You could also write in here, so 1/2 of the natural log of x to the 4th over 2, if you're so inclined to write it like that, plus some c value. Okay, so there's lots of ways that we can express this c value, right? It could have been 2c when we multiplied it over here, right? 2c's, or c sub 3, right? Lots of ways to do that when it comes to the c part of your equation. So without an initial condition, just leave it as c. It really doesn't matter that much, right? So it could have been 2c, right? Lots of things could have happened with there. Anyway, let's move on. So here we have some of the exponential things. It tells us the rate is given to us by an exponential equation where c is measured in millions of cans per year and t starts at 1990. So the rate of consumption, right? That's your rate of consumption is, it triples every 4 years. Triples every 4 years. So if we're going to use our equation p equals c e to the kt, we divide both sides by c. This ratio is what we're talking about tripling. Okay, so maybe we started with 100 as our c value, and now your p value is 300. Well, 300 divided by 100 is 3. Okay, and that happened after 4 years, it says. So we have to make this equation and solve for k. So our first step here, back to pre-calculus, would be to take the natural log of both sides, right, to get rid of our e. So natural log of 3 equals 4k. So then k is the natural log of 3 divided by 4, and there's lots of ways that you can write that, but that's really the only thing that we have to solve for this equation. So potato chip consumption is 8 million, right? That's our initial condition in 1990. So that's your c value, 8 million. E to the natural log of 3 divided by 4 times t the years. Okay, so we have to know that the c value is your initial condition, and then we have to solve for k using our exponential equation there. Let's see what our second problem says. The weight of a population of fungus, well, that's interesting, maybe, maybe not. It tells us the rate is increasing at 100 ounces per day So if we need to write an expression and we need to figure out what k is. Okay, so we know that the rate is 100, so this is 100. Okay, times at t equals 0, it was 50. So we have a y value of 50, which means we have a k value of 2. So if dy over t equals k times y, when t is 0, it's 50. Okay, so we have a k value of 2. So let's see, what else do we need? Y of t equals 50, right? That's our initial condition. E to the 2 is your k value, and t is your variable. So 50e to the 2t. Okay, so what we do is we use your proportional derivative, right? So this is a differential equation with a proportion. We plug in your rate and your initial condition to figure out what your k value is, and then you use your initial condition back in your formula and write down, replace the k. Hopefully that's not too bad. Okay, now on to slope fields. So you're going to have a FRQ about slope fields. So here we have this slope field, right? This means slope. Dy dx means slope of all the lines is x minus 1. So let's look at all these x's. So here we have an x value of 2. 2 minus 1 means we have a slope of 1. So at all these values where x equals 1, we're going to have a slope of positive 1. Okay, here when x is 1, we're going to have a slope of 1 minus 1, which is 0. So all these ones are going to have 0 slopes. Okay, and then 0 minus 1 is negative 1. All these will have negative 1 slopes. Okay, at negative 1, that's a slope of negative 2, so a little bit steeper, but make sure we're making it negative, right? Negative. And then at m equals negative 2, negative 2 minus 1 is negative 3. So even steeper than your negative 2. So that should be what your slope field looks like. They're telling you to find the slope by taking your x value and subtracting 1. Okay, it says draw the solution through the point negative 1, 1. So we're going to do our best to follow these slope curves starting at this point. Okay, so maybe it comes down and it goes to that one, and maybe it flattens out here, right? It's got to be pretty flat when x is 1. And then it comes back up through this one maybe, and it goes out like this. All right, so kind of follow these slope field lines to generalize your slope. So this might be the solution to the point negative 1, 1. Okay. Write the equation of the tangent line. So a tangent needs two things. It needs a point, fantastic, and it needs a slope. Okay, remember your slope is found up here by doing x minus 1. So when x is negative 1, we have a slope of negative 2. So using our point slope form, y minus 1 equals negative 2 times x plus 1. That is the equation of your tangent line. And we're going to use that to estimate f of 0.3. So let's f of x equals y. So we solve this for y, we get negative 2x plus 1 plus 1, right? So if we solve this for y, that means we add 1 to both sides. And now we're going to plug in our 0.3 into here. Okay, so f of 0.3 is approximately negative 2 times 0.3 plus 1 plus 1. Okay, so then let's just do a little bit of algebra. So negative 2 times 1.3 plus 1 is negative 2.6 plus 1, which is negative 1.6. So f of 0.3 is approximately negative 1.6. Right, that's the y value when x is 0.3. Okay, and then lastly, find a particular solution to the differential equation through the point negative 1, 1. Okay, so we come back up to our dy dx equals x minus 1. And we have to separate, so I'll bring my dx over to here. dy equals x minus 1 times dx. Okay, we will integrate both sides, and this is just y. And here we have half of x squared, right? That's the antiderivative of x, minus x plus c. And now we have the point -1, 1. So I'm going to replace y with -1. So -1 goes here. Right, very sloppy. And no, that's not true, is it? Y is +1. +1 goes here, and then -1 is your x values. So -1 goes there and there. Aha. So we have 1 equals half of 1 plus 1 plus c. So it looks like c equals -1/2. So then finally y equals half of x squared minus x minus 1/2. So that's the particular solution for the differential equation that goes to the point -1, 1. Okay, so not too bad. After we got done with those exponential ones, it turned out to be okay. So you will have an FRQ that has a slope field as its main component. Okay, probably a differential equation also. So be ready. That's all.